So Ammar is a principal research manager at Microsoft now. So he leads the DeepSpeed framework, and his talk will be on DeepSpeed and Trillion-parameter LLMs. Can the synergy of MPI and nickel improve the scalability and efficiency? So I remember that was one of his first papers and probably best paper at Euro MPI, if I remember correctly.
Yeah, it was the versus,
yes,
not the combination.
Yes.
I've become more collaborative than competitive than I used to be.
Good. So Microsoft has treated you well. Good. So let's welcome Ammar.
Thank you, Harry. Can you guys hear me clearly? Thank you. Yeah, really glad to be back here, not as a student. And it's been 10 years. So I was telling Sadaf, the first mug I attended was 2014, and this is 24. So pretty excited to be here. I have been at Microsoft for the last 4 years and part of the DeepSpeed team. For those of you who don't know what DeepSpeed is, there's a little bit of an introduction today, but we are mostly about very large-scale LLM training and fine-tuning. That was the scope. Recently, we've also moved to some of the inference optimizations. But primarily in this talk, I brought this specific topic of trying to see if we can collaborate different runtimes, because there is value in having different runtimes because they were built for different purposes. And no one understands this better than, I think, the audience here, and especially the great students that Dr. Panda gets every year. So the title is, Can the Synergy of MPI and Nickel Improve Scalability and Efficiency? But it would not be just to say MPI. I feel like MBAPICH is the best MPI, and we should explore this in the context of MBAPICH. So for some of the people who have been in this space, this a very familiar chart. But for those who you've not seen it, like what we've been trying to sort of focus DeepSpeed is that extreme right area over there. I don't know if this is visible on that, but you can see the 2 years of scope of DeepSpeed is where we're trying to sort of innovate in the space where the hardware is not keeping up with the model size, and hence you're just like blocked by either you have to use multiple of them, or you have to sort of invest in software approaches to get there. And so this chart is just showing how parameter count in terms of billions of parameters is increasing, and the largest of the models, published largest models, probably around 600 billion, which was in the G-Shard paper. And all of those style of models are supported and actually enabled. A lot of them are enabled through the use of DeepSpeed core technology. This is on the training side. Then there is also, we have a work on DeepSpeed inference. So there is LLMs, there's SLMs, there's a huge variety of models being trained. And so you actually have to serve them. And serving is the next major challenge in the LLM space. And so I think half of Microsoft is working on that. We are also part of the sort of larger inference optimization effort now. But this chart is just trying to show how state of the art, which is sort of these red lines over there with Hugging Face, which is what everyone uses to download the models and try them out, is pretty unoptimized for actually serving the models in production. And so that's where DeepSpeed inference provides this benefit. Also, this project has had a lot of open source impact, almost 10x year-over-year growth. 6 million installs, probably a lot more now. I think this is some old data, and more than 356 unique contributors to the GitHub repo. Some of the very esteemed national lab folks are also using this. So we're very proud of this project, and that's what we do. It's also very simple to use and extend, and I think that's where the entire focus of this talk would be, is that I'm going to present this case study through the MCR-DL work that Quentin here actually did with me 2 years ago when we were interning at Microsoft. Yeah, and so the idea was that there are communication runtimes like Nickel, which is heavily optimized for NVIDIA hardware, and on top of that, not just NVIDIA hardware, but also their data center system, which is very DGX heavy. You have lots of NVLinks, and it's also very all-reduce optimized kind of an communication runtime. Whereas there is MPI, which is far more generic. It's HPC, AI, big data. You can do everything with MPI. And so in this work, the idea was to explore this synergy, and I think we were pretty successful in showing. This was IPDPS 23. I think there is a poster out there, so feel free to check that out as well for more details. And so just a little bit of motivation, like we all know large models are important. They need parallelism, and parallelism exists in different flavors. The simplest of regime is data parallel. Pretty much everyone in the room understands it very easily. Just replicate the stuff, communicate the gradients, you're done. But it has limitations. The max model size is fairly limited to the amount of GPU memory you can sustain. And so that's like 1.2 billion parameters. And in today's world, that's nothing. That's a tiny model. 5 years ago, this was extremely large, infeasible model for any company. Even a company like Google was having trouble serving a BERT model, which was just 345 million. So models have indeed become much bigger. What has enabled them is model parallelism, combination of model and data parallelism, a very complex combination of data, model, and pipeline parallelism. What we do at DeepSpeed is what we call ZERO. It stands for Zero Redundancy Optimizer. And more recently, PyTorch has taken up this effort, and they call it FSDP. So for those of you who know more of PyTorch, FSDP is an implementation of the Zero family of optimizations. There is communication, a lot of communication in deep learning models in different ways. And so I think that's where the entire thing becomes interesting for this specific group of people here, especially the research students who are trying to get newer ideas and see where do they publish their next paper, what kind of approach they should be working on or optimizing. So these slides are borrowed from Quentin's IPDPS talk, and here we are just trying to show this deep learning recommendation model, which uses an all-reduce and an all-to-all. MOE uses perhaps the most complex combinations of all sorts of communication, including an all-to-all. And so what we explored in this effort is, let's say if you have an MOE model and you want to train it, is nickel your only solution? And the state of the art when we started this work was PyTorch and DeepSpeed. And they were relying on nickel collectives. And so the all-reduce for data parallelism or 0-3 parallelism was done using all-reduce, reduce-scatter, all-gather from the nickel library. And similarly, the all-to-all also was being done there. And so we did some hotspot profiling, figured out, okay, clearly, these two charts show you that one library has a better all-to-all, the other library has a better all-reduce, but these two runtimes don't talk to each other. And so we can't do that. Either you reinvent the entire all-reduce and other collectives that are much more optimized in nickel for a reason and bring them to MPI, or you could collaborate and think of a higher level out-of-the-box solution. So that's what MCR-DL stands for, is to be collaborative and not really competitive when you don't need to, so that you can push the frontier of performance to the next level. And so I really want to emphasize that this is one of the favorite works that has been done by an intern at Microsoft, DeepSpeed. People have cited this work. They really like the idea. The whole sort of mindset around it is that we can build on top of each other. We don't need to always sort of like destroy the other thing. We can complement, we can collaborate. And hence this topic of like, can we do this in more things? So we talked a lot about our all-to-all. I'm bringing some new work that we've recently published, which we call it DeepSpeed-Ulysses or Ulysses. And this was recently presented at PODC. The idea here is that there are a lot of system optimizations that are needed for this upcoming long sequence models. And to motivate this problem a little bit, long sequences are everywhere. So naturally, when we if you don't know a little, transformer models work on tokenization. You have a lot of data, you tokenize them, that's the input to the model. And so long context LLMs are an upcoming use case. The initial GPT-3 model or the chat GPT that came out, you had a context length of 1K. They extended it to 2K, which means that you can only have 2,000 tokens in your prompt. And after that, it is unable to connect back to it. So if you ask a question from ChatGPT, it's going to lose that context beyond 2,000 tokens. And that's very limiting. So recent sort of like AI space researchers have figured out, okay, we want to extend this context. And let's say if you want to do a book chapter summarization, you can do that with 2K. You can do that with 8K or even 16K sometimes. So the latest model that Microsoft, for example, had like 5.3 with 128K context length. The Gemini model from Google has almost a 1 million context length. OpenAI latest GPT models are also trying to push the frontier of this long context. But it comes with a problem because the systems were not really designed for long context. And there is like a lot of memory bloat, you can say, when it comes to supporting longer sequences. So here, this chart over that right side is trying to show you that if you had a model, this model is a fixed size model, I think 30 billion, and you have 8K sequence length with DeepSpeed 0.3 on 8 or 16 GPUs, you can split it, shard it, and get pretty decent performance of 162 teraflops per GPU, which is almost the best achievable performance you will get on an 800 GPU in any state-of-the-art system. But as soon as you go to 16K, you run out of memory, and there is nothing you can do about it. So you're blocked by that context length. And that's why if you go to Hugging Face today and download any sort of open source models out there, most of them will be under 8K or 4K even, because people just don't know how to train it. And there's no sort of library that trains them out of the box. Then there are systems which support, but then there's a lot of communication efficiency. So there's another system which is a competitor system to DeepSpeed is called NVIDIA Megatron LM. And that framework allows you to do its own style of sequence parallelism. And in sequence, it means prompt, or the tokens, the number of tokens in your sequence is the token length or sequence length. But you can see they're highly inefficient. So 50 teraflops, 72 teraflops, it's very subpar. No one wants to use a GPU and get 70 teraflops when they can actually get 3x more. And they also are a bit hard to use. So DeepSpeed-Ulysses is one of the solutions. And again, this chart is just trying to show you the relative sort of context scale being increasing, and also the model scale relative to the context scale. And the key idea is that we would want to partition the tensors along the sequence and the head dimension. For those of you who know a little bit of transformers, heads are, you can consider that as a dimension, one of the dimensions of the model, and the head dimension is an important one. And what we're trying to do here is that we're trying to spin or change our lens to the problem area and bring it from the aspect of head, because there are multiple heads in a multi-head attention block. And those heads can be exploited on multiple GPUs if you want to support long contexts. That's one of the most sort of, I would say, unique or novel long context solution out there. And what it does is it allows us to do it with efficiency, with memory savings, and it's also attention agnostic. So there are a lot of attention mechanisms published by the researchers. Almost on a daily basis, you will see a different kind of attention getting implemented, or some research work is happening there. So what we have done is taken the core attention block as a block and figured, okay, what if we convert the sequence parallelism problem to a head parallelism problem? And now let's say you have 4 GPUs. In this example, you have 4 GPUs, and your model will also have 4 heads. And then each of these boxes is actually on a different GPU. And so then all you need to do is need to insert in an all-to-all before the attention computation and after the attention computation. And it employs this at the cost of a very expensive collective. So most of the people who are collective communication experts will be like, or don't use all-to-all, it's a bad collective. Or it's a collective that you only should use when there is no other alternative. I think that's what at least the lesson we've all read. But it's also pretty much a collective that rightly fits a lot of natural problems. So we were like, okay, let's do a little bit of analysis. And so there is the existing work, which is O of M, where you can think of M in a very high-level way as the number of tokens in your sequence. And what we want to do is convert that to an O of M by P problem. And that's what this all-to-all does. So yes, all-to-all is an expensive collective. We are inserting it in the middle of things. But the alternatives were far more inefficient. And so all gather and reduce scatter are now sort of, you can see then they are in the order of M. And what we are doing within 2 all-to-alls is that we're just doing an all-to-all with that 3n by P, and then another all-to-all with an n by P. And so you add them, that's the 4. But dropping off the constants, you just see it's an m by P, which means you can scale it. You can scale it as you increase the number of GPUs. So as you have more GPUs, you can almost go an infinite context length. And that's the whole idea behind this. But on top of that, what we did is we already have 0.3, which shards your parameters. And so we said, well, why not combine them? So what we do is we combine DeepSpeed 0.3 parameter sharding, which still uses the standard all-gather to fetch the parameters. But on all the activation partitioning side, we just use this Ulysses approach. And a combination of them allows us to have, at a very high level, a very easy-to-use block. All you need is wrap your attention module into the attention of Ulysses, and then everything else is taken care of under the hood. And so I think sequence parallelism with Megatron had this problem that it was only implemented with flash attention. So what if your hardware doesn't support flash attention? Then you can't use Megatron. Or if you want to implement a sparse attention because you know your problem is in the sparse space. So all of that led to developing this easy-to-use framework. which can scale. We have tested this on 64 GPUs to a 1 million context length, which is a significant thing. If you want to sort of like take up a Harry Potter book, actually all 7 books of Harry Potter, and tokenize them, you will still be able to train your model with that entire 7 books in that particular context, which is a big deal, because then if you can ask intelligent questions about Harry Potter, let's say, this is just a real world example that most people understand. You can think about as weather forecasting or high resolution images or videos, where you will naturally have long context because of the sheer resolution of the model. And so that's the solution. What I want to really emphasize here is that not how great DeepSpeed sequence parallelism is, but it's a food for thought for the students who are trying to understand problems and do interesting research in MVAPICH group, right? Or even researchers outside the MVAPICH group itself, is that there is always a different way of looking at the same problem. And you end up finding out really creative solutions if you don't go too deep and think of it as a broader impact focus. Like, okay, what am I going to get out of this approach or optimization? And so that's where I think one question, I don't know, Dr. Panda is probably a little busy, but my question is, which student is coming to Microsoft for the internship so that they can be the next MCR-DL for Ulysses? Because Ulysses right now is purely all on nickel. We haven't done anything with MVAPICH, and that's where we need a student to come and investigate how does MVAPICH plus nickel or purely MVAPICH compare to a nickel backend-based Ulysses. And maybe the context length increases, maybe it's more efficient, maybe the teraflops increase. All of those are very valid and very novel research ideas that you can write a paper about, publish it, have an impact on real models. So that was this task 1. I just want to quickly check time. How do I'm good? Okay. So that was the number 1 thing that I wanted to present from the DeepSpeed side. The second one is also yet another.
So before you go further, what is the typical size of the all-to-alls that you are talking about?
Good question. I don't know if there is a thing. So the way you can think about it is we will do an all-to-all in the number of tokens divided by the number of GPUs. So let's say if you have 1 million tokens, right? And you only have like 64 GPUs, then you can do the math. So that will be the size of the all-to-all. The first all-to-all will be 3 times NH, and H is the same as the P. So you can, H is just the number of heads. So those 2 cancel out. So you can just think of that as the 3N case. And then that would be the actual message size of the all-to-all. We haven't done a profile, but I could probably ask Sam to share that with you.
But broadly, I think we are looking at fairly large all-to-alls.
Yeah, it will be a large all-to-all, similar to what an MOE, DeepSpeed MOE had. So there is value in exploring different things. You can see that deep learning is becoming a very all-to-all heavy thing as we investigate more fun approaches. So it's
is there any sparsity at all in the all-to-all, or is it like a dense all-to-all?
Great question. I do not know, but let me think about it and get back to you on that. I think that sparsity comes from patterns. I don't know, because we're actually, no, there is no sparsity here because we're actually splitting the entire input. So you would want to keep everything, otherwise you lose context.
Okay. So in that case, my final question on this, is there any potential to overlap any of this all? Because all-to-all, in let's say, unless you are going a weak scaling approach, all-to-all is a very bad for scalability.
Right.
So are there any portions where you think there are 2 all-to-alls before and after? So can any of these be overlapped with independent computation?
Good point. I think the overlap opportunity exists when you convert this purely from sequence parallelism to sequence parallelism plus 0.3 and data parallelism, because there are other collectives happening to gather the parameters, right? So an all gather has to happen so that you have all the parameters. The all-to-all has to happen so that you have all the attention block, and then you do the attention computation. So we haven't explored them because they were all based in the nickel context. So there is a natural overlap because all of them are non-blocking.
Okay.
So you have a buffer, you have a compute attention, then you have an all-to-all that's on the GPU. So we never do a CUDA sync.
Okay. So naturally, it is overlapping.
It's a non-blocking operation. How good of that overlap is there is we haven't studied it.
Okay.
Yeah. So it's a good problem to study, is what I'm saying. Yeah.
Sure. And when you do these operations, what are the CPUs doing in general? Are they idle or are they?
Pretty much idle.
Pretty much idle. Okay. Thanks.
Yes. You're welcome. Yeah, so the second work is what we call 0++. This work was recently presented at ICLR by Hyang, and the motivation for this one is slightly orthogonal to the previous work we did. That was a purely long sequence problem that we were trying to solve. Here, what we have noticed is that large batch size has its limits. So with 0.3, the 162 teraflop numbers that you guys saw, it was based on an assumption that you have a large enough batch size that you can actually let the GPUs do some work and then communicate. What we notice is that communication will become a significant overhead. If you think from this chart, if you look at this chart, 8, 16, 24. So as the per GPU batch size increases, your orange or the communication overhead reduces. And that's the expectation, right? But there are real world problems where the large batch size is bounded by the actual model quality. So you can't really just keep making the batch size bigger. And so what will you do if you were in the regime where 8 per GPU is actually fairly large? We've seen cases where we can only do 1 per GPU. Because if I want to use 2,000 GPUs and I do 1 per GPU, it means my overall batch size is 2K, which is a very large batch size to train a large scale model with the Adam or LAM. And so hence we are naturally bounded. This is not a problem that you can resolve, so you have to sort of like do something with it. And this communication overhead, as you can see, is almost 50%. So what do we do about it? Again, going back to the same principles, what do? You just analyze where is the communication volume. In the standard 0.3, because we use a all-gather collective to aggregate the entire global GPU memory space of all the GPUs, we need to fetch them. And when we fetch them, there is a forward all-gather on weights M, there is a backward all-gather on weights M, and then there's a backward reduced scatter on gradients M. So there is a total communication volume is 3M. Now, what we want to do is we want to reduce the volume so that we can do more efficient. Because it works, it's just not very efficient. So the first thing we do is, how do we reduce the forward all-gather communication? The easiest approach that someone investigated in state of the art is, well, we can communicate in 8-bit quantized weights. We don't need to exchange all the 16-bit weights. We can quantize them to 8 bits and do it. But if you see the blocks on there on the right-hand side, if you quantize data at the full scale, full tensor level, what happens is that you get up a very huge error, and you can see these red numbers trying to show that there is massive quantization error if you just do the full matrix quantization. So what we introduce in this work is what we call blocked quantization, and you can think of block size as a hyperparameter. So you have to really tune the block size. But in general, this is trying to show if you have a larger number of blocks, the quantization error reduces significantly. And so just a question for the students here, what do you think would be the best block size or best number of blocks to have 0 error? Does someone want to look at this graph and answer that question? You have 1 to 2K number of blocks, and you can see the Euclidean distance or the quantization error is reducing as you increase the number of blocks. So what is the max blocks you can do? That's a question for anyone, actually. This is just a math question. You have a matrix, right? And you have number of elements in the matrix. So what's the smallest granularity at which you can quantize? Quantize each element in the vector separately. That's the max number of blocks. And the benefit of that is you will get very fine-grained quantization, but what's the problem? The problem is that it will be so expensive then that the benefit of quantization will be completely lost. We were doing quantization for a reason, not for fun, right? The reason was we were trying to reduce the communication volume so we could go faster in the collectives. If you take so much time to quantize the tensor or the vector, you're just not going to get it. So that's why you have to really carefully tweak it. And the overall idea here is that your communication reduction in forward pass goes from M to 0.5 M based on some of the heuristics that we used to quantize it and not introduce an extra overhead. And the 0.5 comes from the fact that we're now doing 8-bit instead of 16-bit. The second part is now that you need to do reduce backward all gather, how do we change that? So this is the most interesting part of this effort, and what we call it is called heterogeneous partitioning. What we do is we model weights within the node and rest across all the nodes. And all gather will just only happen within the node. And in the DL space, typically any intra-node communication on DGX, we just consider that zero communication. So whenever we talk about communication, every time the analysis is done, it's inter-node communication because that's more expensive. And so here we just eliminate the backward all gather completely across nodes, and we do it just on the intra-node. So the backward all gather communication goes to 0, and hence the reduction from 3M to 1.5M. And finally, you reduce the backward reduced scatter comm by, can we quantize the gradient communication? Well, we can, but the problem is there is a precision loss because the reduction itself is an op. So it's not like all-to-all where you're just exchanging the data, you're also doing an actual reduction. So if you do reduction on the quantized data, it becomes very lossy, and the precision is lost. So that cannot be done. What we do is instead, again, look at the problem differently and introduce an all-to-all to replace the reduced scatter and communicate in lower precision, but then reduce in full precision. So it solves multiple sort of like challenges in terms of like convergence studies and model quality and whatnot, but also reduces the communication volume by another M to 0.25M. So from original 3M, now we have gone to 0.75M. And someone could say, yeah, sure, you have reduced the communication volume, but now you're using a more inefficient collective too. We know the bandwidth that we can get from the all gather is never going to be equal to the bandwidth that we get with an all-to-all. However, I'll tell you why it is still more efficient. So from a system design perspective, what we saw was that, okay, how can we quickly do this, right? And the problem is there's no existing collective for quantized gradient communication, like you have to rewrite it. There is this very readily usable scheme we called one-bit Atom. In fact, that's the first work I did at Microsoft for DeepSpeed. But that cannot be applied at 0.3 level because you need the entire model to be there in memory to do one-bit compression scheme. And then if we try to directly apply quantization on reduced scatter, it will have a longer latency and a lower precision itself because it's sort of ring-based, so it accumulates. So that's what we call the too many quantization problems. So what we did is replace the ring-based reduced scatter with one hop all-to-all and see, okay, this all-to-all can do the same thing we want to do, but not in a ring way. So we quantize, we do an all-to-all, then we dequantize plus reduce, and hence we get the same result. There is another challenge that just sort of stems from that previous optimization is that the communication volume will blow up. And so how do we deal with that? I think that's a very simple solution. Pretty much everyone here understands this very intuitively, like let's do a two-level collective or a hierarchical collective. So we do a hierarchical all-to-all, but doing that also has another implication, which is what we call data misplacement. So the data is now not in the right positions. And one of the things that you never think about doing an all-to-all in this way and on CPUs is because these buffers, it takes time for you to exchange or do this thing. But with GPUs, everything is a kernel, and they're very fast and efficient kernels to actually just do a small transform. And so when you do that transform, you can actually get that data back into the original ordering, and hence we sort of like solve this problem in these three different optimizations stacked on top of each other. And finally, once we have this from an end-to-end perspective, what we saw is that all of these could actually be fused because each of these things or steps that you see from top to bottom is a CUDA kernel. And so you can do them in different streams, you can combine these operations, you can do slice reordering and quantization in one block. So the yellow boundaries are here just trying to show you the fusion. And sort of then there is an intranode all-to-all, then do another dequantize reduction quantization, and then do an internode all-to-all. So with all of this combined, you can very easily get a lot of benefit. It seems like, wow, you're introducing so many steps, but the end-to-end results show a completely different story. In fact, you just get almost like 300% speed up if you had a really terrible network bandwidth. No longer people use this, but like even on a very decent like 100 Gbps kind of Azure networking, which is very common still on the clusters with 8 GPUs and so non-DGX boxes, you could get almost like 2x speed up. And hence, my sort of like question back to the students, think about what you can do with this because there is again a mix of collectives. So this theme of combining different communication runtimes is occurring again and again, and it's increasing. So when Quentin and I did this MCR-DL work, we were actually struggling to find out an actual use case where we could plug in this approach and say, hey, an all-to-all from MBAPICH and an all-reduce from nickel would combine really nicely. But now we are naturally moving into that scheme. And so my food for thought for all of the people in this room is, let's explore MBAPICH plus nickel and see if we can unlock the next level of performance for more sophisticated parallelization and quantization schemes to train LLMs of the future. I also want to give 3 small sort of snippets from what I've learned while I was a student at Ohio State versus what I learned at Microsoft is that there is, as a student, we always have a publication first mindset. And that mindset sort of sometimes tells us to tackle problems that are not too hard. Because if you're attacking a very hard problem, you might not get a publication in the first shot. And so then naturally what you try to do is reduce the scope of it and say, this will give me a paper now versus, oh, that's a really long-term project and probably I'll have to work 2 years and not get anything out of it. But that work that you will do with an impact-first mindset will end up becoming far greater than anything you can do with even 4 of low-impact papers combined or 10 of low-impact papers combined. Because you're actually solving a real problem. And people would flock and use such techniques. So focus on that. The other thing that I've also figured out a lot during my Microsoft work is building on top of things is totally okay. You don't need to build things from scratch. So reuse components if you need to. I think that strategy is very well understood at the MBAPICH team because we have this MBAPICH infrastructure. We try to build things inside it and leverage the existing base. But just want to give that as a food for thought for the students. And finally, this is very interesting. So a lot of times we say collaborate and not compete because it helps to collaborate where it makes sense, right? But that does not mean that you should never collaborate and compete. The good example is nickel and MBAPICH again. So you can collaborate when it makes sense to do that, but you should absolutely compete and say, we can go get the speed of light because we are doing the right optimizations. They are hard, they are high impact. A lot of people will use your high impact optimizations if you make that choice. So with that message, I just want to say good luck to all the hardworking students here. And we at Microsoft are looking for people and organizations to support the open source DeepSpeed ecosystem. If you want to go and make a pull request. Unfortunately, the project after 3.5 years of full expansion and support finally maybe sunsetting at Microsoft level. But there are a lot of researchers who moved from Microsoft to this company called Snowflake AI, and they actually lead the Snowflake AI division. That's where a lot of DeepSpeed PRs and new optimizations are actually coming from. There are also still 3-4 people within Microsoft who are going to be actively maintaining DeepSpeed, but we're not able to sort of invest and expand it. So if there are classical ideas, research-heavy ideas that you guys would want to push, feel free to sort of adopt the DeepSpeed framework and fork it, change it, and we're happy to collaborate in a research capacity with anyone. Thank you. Thank you for listening.
Questions for Awan? So I have a question about the 0++ paper. So you've shown very good improvement over the baseline, but how much of this improvement is actually coming from the quantization versus the hierarchical partitioning?
Great question. This chart is going to tell you, so QW is quantized weights, QG is quantized gradients, HPZ is hierarchical partitioning. And so you can see these bars are telling you what's the baseline, what if you do QW, what if you do QG separately, what if you do HPZ, and all 3 combined, they compose with each other. So all 3 composed will give you that orange line, which is what we call 0++. So each of them have their own different benefits in different spaces.
So does that mean that with low bandwidth networks, it seems that HPZ, the quantization is the orange bar, is it?
Sorry, repeat that one?
Is the quantization the orange bar in this?
No, the orange bar is just the combination of all 3 approaches.
Okay.
Yeah, that's accumulation of all 3 approaches. So there are 3 optimizations, right? QZ, QG, HPZ.
Yes.
These combined is what we call 0++. So there are places where one approach will give more benefit versus the other, right? And there is also the impact of network topology. So like which network you use depends on that. Like if the GPUs are much faster, quantization is much faster, right? So the overhead of introduced by quantization will be less, but then if the network is bad, you will end up saving a lot.
Okay, thank you.
So with the hierarchical R2R, assuming it's mostly on the smaller message spectrum,
the message sizes here should be of the order of the model dimension. So it's not small. It's not small. Yeah.
So if you are doing hierarchical, don't you run into like memory issues in the node to stage the additional data?
We typically do not, because I think the way it's done is it's done in the context of 0.3. So it's already sharded the model across all the GPUs. So the buffers themselves are not that big that you cannot accumulate them. So we're trading off, right? That we have a lot more memory now because we're using 0.3. And this is a small batch size problem, right? So you can think of that. So it nicely complements.